are basically giving you a, so this 2 stress capture all the in-plane component of stress, because you can always reduce that to the eigenvalues. Your in-plane stress, sigma 1, sigma 2, tau 1, 2, will result in these two. I'll double check. I don't remember it may be the in-plane shear. Let me double check here. Tau 6. Yeah, it's in-plane shear. So I'm sorry, that's tau 6 is in-plane shear. I was wrong. So this is sigma 1 is it's not a principal stress. It's a stress in fiber direction. So I was confused with this. This is a principal stress. This is not a principal stress. This is a stress in fiber direction, stress in matrix direction. This is the in-plane shear stress. So basically this combination. So one of the ad hoc theory proposed that if you combine these stress like this, you make them equal to 1, let that capture the failure boundary, and then you just fit these parameters. You use the experimental data to find what A, B, C, and D are. That's the theory assumption. All right, so you can use the conditions that the independent test. For example, if you make sigma 2 and tau 6 equals 0, and that's uniaxial tension, you just pull the material in fiber direction. What happens? The material fail at F1. F1 is the material failure stress, right? That's one of the independent tests we do for composite. You get 6 parameters, 5 or 6 parameters. This one, sigma 1 T. That's the independent test you do, and then you pull in fiber direction, and then when the stress reaches this level, it breaks. Right? So imagine you run a test. You put that result into this equation. In this equation, your sigma 2 is 0, tau 6 is 0, and these 3 terms equal 0. So when this A sigma equal to 1, and then the A must be 1 over F1, right? This is a backward estimation. You basically say A sigma 1 squared equal 1. This is a failure condition. And I know A F1 T squared equal to 1, right? You know, when this equal to this, it fails, right? Then your A is 1 over F1 T squared. Now, which is this one? Right here. It's just A. This is the parameter for. So similarly, you can apply this to the other terms. Right? You can apply the second independent test, which is a second. You pull the material in the 2 direction, and then you fail when this sigma 2 stress matrix reaches this threshold. It fails. You can determine what B is. Okay. And so on and so forth. The only catch is that the fiber direction, tension, and compression have different failure thresholds. You pull it, it fails at a certain level, and it compresses at a different level. So you have to differentiate these terms. When sigma 1 is positive, you use F1T. When sigma 1 negative, you use F1C. Right? So this is F1T. This is F1C. They're different, okay? And you can determine these coefficients. That's a failure theory. And then if the stress, none of the stress are zeros, there are different combinations. You just put a different stress in those slots, sigma 1, sigma 2, and tau 6. Again, you have to make this decision which number you use depending on the sign of the sigmas. Okay. If sigma 2 is negative, you got to use F2C, compression, right? And tau 6 doesn't matter. It doesn't matter which direction it is. And you can, because to implement shear, there's no difference. Doesn't matter which direction you shear it. And you plug your stress component in this equation and see how close to 1. If it's a 1, it's failure. So this is a Tsai-Hill failure criteria. Tsai is a professor. I think is still alive. He's a professor at UC. I would say UC Berkeley. He's a famous guy doing composite research in 60s, 70s, 80s, things like that. Yeah, when I was your age, I went to the workshop. He was giving us a week-long workshop on composites. Now he's maybe 90 or 100 some. He's his professor. He came out with a number of theory. Two of his failure theory got very famous. Almost built in other commercial codes. If you buy a commercial code in composite design, they have his failure theory built in. Tsai-Hill and Tsai-Wu. Tsai-Wu is not the failure theory this professor came up with. Okay. The idea is very simple. You just propose. You make a guess what the form it is. And then you fit the parameters. Okay. So it's not quite elegant. The reason that Tsai-Hill didn't feel this theory is the ultimate theory because this thing. You had to make this kind of choosing your parameter based on a sign. It's not very elegant. So he later on he basically proposed another form of theory with a bigger polynomial. He basically assuming all the interactive term contributing. Interactive meaning that different stress multiplied together. If these two stress interacting, there's non-zero coefficients. So he basically turned in the full matrix. He assumed the most general form of the second order failure theory with all the cross terms turned out. There are many parameters. Okay. And use symmetry, you can simplify a little bit. Even you simplify a little bit is way more complicated than the Tsai-Hill theory. So this is basically the difference between Tsai-Hill and Tsai-Wu is Tsai-Wu turned on all the interactive terms. Fij, sigma, sigma j, sigma I, sigma j. There are many terms. Okay. For in-plane stress, simplify from Tsai-Wu, we need to find a way to determine all these parameters based on the independent experiment. Otherwise, it's useless. You have to have a logical way to determine these parameters, F terms. Okay, F terms is what you use in the code to determine how strong this lamina is. You have to have a physical basis to pick those. Those came from experiments. You run certain tests and certain low stress, you find the failure stress with big F. Big F is the experimental results. You have to use a finite number of experimental results to determine what the F terms are. Similarly, you can assume sigma 1 is non-zero, other terms are 0, and you have basically now you can capture difference between tension and compression because when you have a tension, this term is positive. When you compare this term negative, so you basically have two equations. Let me explain this. This is the advantage of Tsai-Wu. You don't have to pick different coefficient of different stress anymore. Assuming that you try to determine F1. Now you have two conditions. Once you pull the composite in one direction, or you pull it, and that gives you F1T. All right, you pull it, and you compress it, and that gives you F1C. All right. So you try to use this two conditions to determine what F1 is. So you put the condition in. Sigma 1 is a positive plus F11 1 squared equals all the term is 0, because other cross terms sigma 1, sigma 2 being sigma 2 is 0, so it's 0. Sigma 1, sigma 3 because sigma 3 is 0 is 0. So all the other terms is 0. But this is equal to 1. Okay. So when sigma 1 equal to F1t, F1t plus F11, F1t squared equal to 0. So this test gives you this equation right here. And this test, F1c, all right, plus F11, F1c squared equal to 1, right? Now this test gives you this equation right here. You have two equations, tension compression. And you solve these things. There are two unknowns. Two unknowns are these, F1, F11, and the solution are these numbers here. F1 equal to that, F11 equal to that. And you can determine these terms. Where is it? I lost my clicker. Oh, right here. Similarly, you can apply the test in two directions. In the matrix direction, you have tension compression. You can determine these terms, and this is a outer plane direction. And these are shear conditions. This includes outer plane shears. For in plane, it's simpler. For outer plane, it's include these things. You in plane shear and two outer plane shear. You have two outer plane shear strengths and one in plane shear strength. All right. Long story short, when you figure out these numbers, you can basically have all the coefficient of the second order polynomial determined. Then when it's time to tell whether the ply is safe or not safe, you plug in stress into this equation. You don't really need to choose your coefficient anymore. Each coefficient is really uniquely determined. You don't need to choose coefficient based on tension compression anymore. You just put your stress in. Doesn't matter. If the stress is positive, tension, you put a positive number in. Compression, you put negative number in. And this give you a failure envelope, which look like this. Okay. It is depending on the shear. If there's shear, basically, if there's no shear, k equals 0, which is this this envelope. When there's shear, this circle gets increasing smaller. So basically, the stress state within the envelope is safe. Outside the envelope is not safe. These are sort of validated by the experiments. People have done over the years validation of these things using a lot of tests in different directions. So this is one of the most popular failure series. If you check Abacus or whatever analysis code, you find these programmed in. All you need to do is provide the input. You need to provide these big F numbers into it. So you determine all these coefficients. Okay. Any questions? All right. These are newer failure series. There's the latest failure theory that people invented. So this is actually basically assume the composites actually fail in two different modes. Okay, they're not related. So they're not trying to use one single polymer to capture all failure mode. So Psi Wu is a polymer that captures everything. All failure mode, all 5 or whatever, is captured by a single polynomial. And this series says you don't need to do that. You just assume that there will be two modes. One of them, they're distinct. Okay, one of them is called a fiber control failure mode. The other is inter-fiber failure mode or matrix controlled failure mode. Okay, it differentiate. If it's a fiber control failure mode, you use a set of equations. If it's a inter-fiber control failure mode, you use another set of equations. All right, and then you have a failure theory like that. It's simpler than the Tsai Hill or Tsai Wu. but you have to make a predetermination what kind of failure mode will occur based on your empirical knowledge. If you know this, this loading condition with this layout produce fiber control failure mode, you just directly go into fiber control failure mode. All right, so that's the 3 different kind of failure series. The simpler kind, non-interactive, the interactive type, and then failure mode based series. Now, how do we use them with DLT code? We can basically put in the failure analysis as a part of the functionality in your code. When you, somewhere in your code, you solve the stress in the material coordinates in every layer. You have that data somewhere in your solution process. And then in that, once you have that, you can start checking each layer by applying a failure theory. For example, Cai-Wu, you just calculate the metric, failure metric using Cai-Wu. For every layer, you can see how far is it from failure or has already failed. Okay. All right, this is some of the characteristics. The very nice summary table for 3 different kind of failure theory. For the first type, okay, it's a simple formulation. Is simple. You basically you don't need a lot of tests either. And Cai-Heal, you have Cai-Heal, Cai-Wu, second order polynomial. You usually need a biaxial test. You need a biaxial test pulling the material in 2 directions to help determine some of the coefficients. So you need a comprehensive experimental program to determine all the parameters. Cai-Wu is notoriously needs a lot of parameters. If it's 3D Cai-Wu, you have a huge number of parameters you have to determine from experiments. 2D is a little simpler. Okay. And the mixed mode, it is basically you have to make a guess what kind of failure mode will occur or make some assumption. And test-wise, it's simpler to do. You don't need to do the biaxial test. You don't need to do a lot of comprehensive experiment to verify, to determine the parameters. Very few parameters for the mixed failure theory. These are some of the verifications to compare the performance of different failure modes, how well they predict the actual behavior, which is the dots. The dots are the actual behavior of the material. So you basically, you have angle ply, unidirectional, you pull it. These are actual failure points you determined. And then you apply the theory to this material, you find the maximum stress, maximum strain theory is the solid line here. So it actually there's some quite difference, especially when you have a jumping of failure mode. This is the region where you have failure mode switching. Failure mode from fiber control in this direction to the matrix control in this direction. In between, you see maximum strength strain curve, you have largest error. In that region, doesn't work very well. You make a prediction which is actually now conservative. Your true stress is lower than the prediction. You can see the 2 interactive theory works better. The 2 interactive theory are Cai-Heal and Cai-Wu, which are the dotted lines. Okay, especially Cai-Wu fits the data beautifully. This is a longer dotted line than this one. Okay. This is a different way to plot the data. This is when you have a biaxial stress. You have also a shear stress. You have a sigma. You have the in-plane shear here, and you have sigma 2. And this is the failure envelope. Again, the dots are the experiments. The lines are the theory. Again, you can see based on the data, the Cai Wu seem to be closest to the data than anything else. Cai Wu theory and then Cai Hill theory, maximum stress strain theory. So maximum stress strain theory is not such a good theory to use. They can be pretty far away from the reality. Okay. More verifications. This is for glass epoxy. This is the carbon epoxy, glass and carbon. Okay. Long story short, Cai Wu seems to stand out in all these materials. Okay. Now I want to show part of code that I programmed to use these failure theories to do the failure analysis. Okay. And eventually, I want you to program this into your code as well. This is a little bit ahead of you, but you are working on your CLD and ABD and stress calculation for now. But once you have that, you can play with the failure series. So I programmed Cai Wu in this code. So to determine the Cai Wu coefficient, I need the parameters here. These are based on experiment data. Okay. So I started with a code that with these functions. Given layup, I can calculate ABD and matrix, different matrix and stress and everything. For each lamina, I carve out these space to store its strength properties. These strengths could be defined for each layer. So these are tensile stress and fiber direction, compressive stress fiber, tensile matrix, compression in matrix, and the shear. And these are the experiment data. Okay. Then I use the experiment data to calculate these Cai Wu parameters. There's that equation you can use. You can calculate these parameters. All right. Then I calculate. So for every layer in my code, I calculate its stress in the material coordinate system. I arranged my code in Excel vertically. So this is a block for layer 1 and block layer 2. And for each layer, I calculate its stress in 1, 2 direction. This will be the stress fiber direction, tension, stress matrix direction, tension. This is negative, that means compression, right? And that's the shear. This is at the top of the layer. This is the bottom layer. I calculate because there are different Z's, one on top and on bottom. They're slightly different. They don't differ by a whole lot. They're slightly different. Actually, the difference in these two are so small, they are identical. If you look at on the 4 significant digit, they're identical. You see, okay. All right, and then I just calculate the Cai Wu failure criteria. I take my parameter, multiply S1, parameter multiply S2, parameter S1 square. These are the terms in Cai Wu. And this is the sum of the Cai Wu failure criteria. I add them up. Now, when this number equal to 1, that means you're at the threshold, right? So I just look at this number. I can tell which ply is closer to failure. So at this state, and that's pretty far away, right? 0.18, 0.18. This is even further away, right? Pretty far away, even further away. Now, once I change the load, once I increase the load, this is at this load. This is a uniaxial load. If I increase load, this number change. I can figure out what load it takes to break one of the layers. I can just do experiments by dialing different numbers. I also implement other failure theory. In this case, I also implement the maximum stress failure theory, which is given this. The maximum stress failure theory is very simple. You just compare the stress in that direction with the strength in that direction, right? I compared the strength to stress. This number, so I calculate a number. This number is a ratio of the material limits with the current stress. So you can interpret it this way. So this number 8.19, it means I need to scale up the stress in two directions that much more to reach a failure point. So the bigger number means that it's pretty far away from failure. Okay. All right. Now, I did a little bit of a numerical experiments. Instead of applying stress in x direction, I apply stress y direction. That's a little bit higher stress here. So everything now changed. I bring several layers much closer to failure now. It was 0.186, now it's 0.471. It just halfway through failure points. This layer. And this one is 0.621. That's even closer. All right, so overall, this is much closer to failure. And this is when I apply shear. The effect of shear on the failure threshold over here. This seemed to be very low load. This level of shear for this ply really is scratching the skin. It's very low load. It's not even close to the failure series, the failure threshold. Bending actually puts high load on the top and bottom layer. You bend it. When I apply bending, what happens is I bring this layer now, especially the top of this layer. This is the top and this is the bottom. Very close to this threshold. And other layers are a little better, but this layer is about to fail right here on the top. Okay. Another bending. This bending causes high stress in the bottom layer, in this layer. This layer is relatively higher than the others. Bending y directions. All right. So it's pretty straightforward. You just apply your theory. You can calculate it. You can make a decision. That's not the end of it. What's more interesting is you can actually predict the failure sequence. So when you have a layup, you can load it so much so that one layer actually fails. For example, you can load the material by jacking up some of these loads under a certain mode. So one layer fails. It turns out that if a ply fails in the matrix dominated direction, if the material fails, the matrix are cracked, it doesn't lose much stress in fiber direction. You become loose bundle, but when you pull in the fiber direction, the fiber remains strong. It can still carry load. And what happens, the internal stress will redistribute. If your matrix cracked up, then your matrix direction stiffness, the E2 will be very, very small. What you can do is once your code determines this threshold, your material failed, you lost a certain layer in terms of E2, you can modify the E2 in that Q matrix. You can reduce E2 to very close to 0. You calculate a new Q matrix. And then you update your entire CLD code to calculate a new stress distribution. The stress redistributes. And then you calculate a new set of stress, which actually a different layer will see high load. And you can test what will be the result of that. Maybe that caused another layer to crack. If it's again the matrix dominated, you can do that again. You can reduce that matrix stiffness by a certain value, and you keep going until you see at a time the fiber fail in certain layers. Once the fiber fail in one direction, pulling failure, the whole laminate considered failed. It doesn't matter which layer. Once the fiber crack under tension or in one direction, the whole laminate considered failed. So you can carry out a sequence. So you basically use the code to predict the sequence. When you do a laminate mechanical test, this behavior show up in experiments. You can pull it or complex layup. You can detect at a certain point, a certain layer gave up. But your laminate can still carry more load because load is carried by other layers. But you can detect a bend in your stress strain curve. Your stress strain curve is not straight anymore. It's a certain bend. And it can bend several times before final failures. And those behavior can all be captured by CIT code. Your CIT code, you just trace through the failure criteria, the failure sequence. You update the matrix and you recalculate maybe 2-3 times. You can retrace that failure curve. You can reproduce the experimental results. Okay. That will be the last project I want you to do. I'll give you a set of conditions. You want to do your CLT analysis. I want you to predict the whole failure sequence. From the first ply crack, second ply crack, third ply crack, and you want to predict which ply cracks, what sequence, and what is the laminate matrix, stiffened matrix after a crack, and what's the stress distribution after crack, and keep carrying on until you see a fiber failure. Okay. And at that point, you reach the strength of laminate, the whole thing, which is limits. And your code should be able to predict that for a certain layup. All right. Any questions? How did it go with your code? How many people have validated the 2 cases? You did? Are you ready to use your code to do the exam? What's the date that we said we're gonna Monday? Oh, Monday. Yeah. Okay. Any questions regarding? I'll check my notes. I forgot actually. Is it? I remember it's a Monday. It's not next Monday. Oh, okay. I see. All right. Okay. Any difficulties encountered in writing your code? Okay. Anybody started homework design? Basically, I asked you to calculate ABD matrix, different type of layout, anti-symmetric, symmetric, and quasi-isotropic. Finished? Anyone finished? Still working on it? Okay. All right. I'm finished what I want to go through today. If you guys have a question, I'm happy to answer it. If not, I can just wrap up. You can work on your code or things like that. Any questions? Let's see if there are any questions from the online people. Looks good. All right, I'm gonna stop a little early today. I'll upload these 2 sets of slides on the website. You can use it to program your failure criteria.
Hey, Addison. Have you texted an email? We just had a buyout through automation and didn't have access to the support groups or website.
Saturday.